In this video, we are going to be discussing on organic nitrogen compounds. I'm talking of amines. We will discuss the amines, then followed by amino acids. But before we continue, I want to appreciate those of you who have taken time to subscribe to our channel. You have really motivated us. Then for those of you who haven't subscribed, please motivate us by subscribing to our channel. And do not go without hitting the notification bell. Thank you once more for taking your time to subscribe to our channel. Let's get started. As I said, we are going to treat organic and nitrogen compounds, the amines. What are amines? Yes, we can say that amines are organic derivatives of ammonia. They are organic derivatives of ammonia in which one or more of the hydrogen atom on the ammonia is replaced by an alkyl or by an aryl group. As said, amines are, you can say amines are organic nitrogen compounds, or you can say these amines are organic derivatives of ammonia, in which one or more of the three hydrogen atoms is replaced by an alkyl or an aryl group. It should be noted that amines are classified as primary, secondary, and tertiary depending on the number of the alkyl groups or the aryl group that are connected to the nitrogen atom. As primary amines, you know, primary amines have an amino group. They have an amino group bonded to an alkyl or an aryl group. They have an amino group that is bonded to an alkyl or an aryl group. That I'm talking of an aromatic group. An example of these primary amines are things like we can call them methyl. Example. Let me just give the example here. You can have a compound like this. NH2. You can have another compound like this. Can keep on, the carbon chain can keep on increasing. All these are all these are all examples of primary amines. You have these, you have methylamine, you have ethylamine, you have propylamine, you have phenylamine. So as I said primary amines, they have an amino group that is bonded to an alkyl group or to an RI group. This is an amino group that is bonded to an RI group here. This is an amino group that is bonded to an alkyl group here. Amino group bonded to an alkyl group here. Amino group that is bonded to an alkyl group here. All these, we say they are all primary amine because only one of the nitrogen on the ammonia has been substituted. Again, we can go an example of a secondary amine. Again, here, as I said, only one of the nitrogen. Here, you will see something ammonia like that. Here we have only one of the nitrogen. Excuse me. Here you can see. Here you will see that generally we have hydrogen. We have hydrogen, and here we have an alkyl group, and this alkyl group represented by arrow is represented by, it could be a methyl group here, it could be an ethyl group, this ethyl group here, it could be a propyl group here, or it could be an RI group here. All of them are attached to the amino group. This is, you can write it like this. So you see this, which is all of them are attached to the amino group. In that case, we say this is a primary, all of them are all primary amine. Again, we go to secondary amine. Secondary amines, they have two alkyl groups or two RI groups, attached to the amino group. In that case, we will have something like this. In that case, we have something like this attached to this. Something, two of them attached there. So, an example of this, as we said, this is, we have a hydrogen, we have a hydrogen, and we have a hydrogen. And when two of the hydrogen groups are substituted by an organic, by an alkyl group or an RI group, in that case, it gives rise to what we call a secondary amine. Take for instance, we have two methyl groups substituting the hydrogen. We are going to have here two alkyl groups substitute the hydrogen. Let's say this is, we have this as a methyl group, and we also have this as a methyl group, and we have this as this one. We have our hydrogen here, which for simplification you can still write it like this. For simplification, you can still write it as a CH3 NN This is an example of a secondary amine. Two of the hydrogen on the nitrogen on the ammonia have been substituted by an alkyl group, and in that case we will call this. In that case, we call them secondary amine. They could also, if three of the hydrogen if 3 of the hydrogen are substituted, in that case, we are going to a tertiary amine, where 3 alkyl groups or aryl groups are now attached to the nitrogen atom. We now call it a tertiary amine, and that would, in this case, that will result in a trimethylamine. It will result in trimethylamine. In this case, we have, let me say, in this case, we have something like this. We have a nitrogen, as usual. And this, all the nitrogen atoms on all the hydrogen atoms on the nitrogen are now substituted by alkyl group, by an alkyl group, for instance, a methyl group. Like in this case, we will say this nitrogen here is a methyl group. This is a methyl group. This is a methyl group. It's a methyl group, which we can even write like this, which we can even write as CH3, CH3, 1, 2, 3. There are 3 of them. Then a nitrogen. In that case, all are the same. In that case, we can call this molecule, a trimethylamine. A trimethylamine. A trimethylamine. Just the same way, like this one up here, which could have still been like a CH2. This one could have still been like a CH3, 2, and H. In that case, that is a dimethylamine. So in that case, so we call this a secondary amine, and at the same time we call this one a tertiary amine. That is how amines are being classified. That is how amines are being classified. If you see amine in this order, that is how you find them. So, as I said, amines are organic derivatives. These are organic derivatives of ammonia. Organic derivatives of ammonia, in which 1 or more of the 3 hydrogen atoms are replaced by an alkyl group or an aryl group. So they are all derivatives of ammonia. You have seen the alkyl groups and the aryl group substituting the nitrogen, leading to the different groups of the amines. We said it is a primary amine, it is a secondary amine, it's a primary amine, it is a secondary amine, and it's a tertiary amine, depending on the number or how many number of alkyl groups are substituting the hydrogen atoms on the nitrogen. If one alkyl group substitute only 1 hydrogen, or if only 1 hydrogen is substituted by an alkyl group, in that case it leads to a primary amine. If 2 hydrogen are substituted, or 2 alkyl groups substitute 2 hydrogen atoms on the nitrogen, in that case we are leading to a secondary amine, like in this case of dimethylamine. If 3 of the hydrogens are being of the hydrogen on the nitrogen are being substituted by an alkyl group, in that case it leads to a tertiary amine. And in this case here, on our example here is given as a trimethylamine. So now we will be moving straight. We will be moving straight to the basicity. We will be moving straight to the basicity of the amines. We will be moving straight to the basicity of amines. So before we get there, we can summarize. We can summarize amines to be as let me put it in this way. We have R, yeah. This is a hydrogen. This one is a nitrogen. R prime. This is hydrogen. And this is N. We have nitrogen here. What is this? And nitrogen. This R prime. This arrow, and it is double prime. You will see that this is a primary amine. This is a primary amine because only one of the hydrogen is substituted. This is a secondary amine. Because only the two of the hydrogens have been substituted, and this is a tertiary amine. Because 3 of the hydrogen have been substituted. So next, if we now go to basicity, the basicity of amines. We said the strength of the basicity, the strength of the basicity of amines, or in other words, we can say the strength of ammonia and other amines will depend on the availability. It will depend on the availability of the lone pair of electron on their nitrogen atoms to bond with a hydrogen ion. So now, for an amine to be more basic than the other, it would all depend on the availability. It will all depend on the availability of the lone pair of electron on the nitrogen. Availability of the lone pair of electron on the nitrogen to form a dative covalent bond with a hydrogen ion. Remember, according to Bronsted-Lowry theory, of acid and bases, bases are proton acceptors. And acid are proton donors. But on the other hand, according to the Lewis acid base theory, bases are classified as electron pair donors. According to Lewis, bases are classified as electron pair donors. But according to Bronsted-Lowry theory of acid and bases are proton acceptors. So we are going to use it here. So since we are saying that the basicity of the amines will depend on the availability of the lone pair of electrons, on their nitrogen atom to bond with a hydrogen ion. Here, the lone pair of electron on the nitrogen is going to be used to form a dative covalent bond. In that case, we will be Lewis acid base theory will be playing a role. In that case, Lewis, I said in that case, the Lewis acid-base theory will be playing a role, because bases will be bases are classified as electron pair donors. They will donate their lone pair of electron to the hydrogen ion. They will donate their lone pair of electron to the hydrogen ion. So, for a base to be strong, there must be that availability of a lone pair of electron on the nitrogen to donate for bonding. There must be that availability of the lone pair of electron on the nitrogen to use for dative covalent bond with a hydrogen ion. But for this, there are some, because if you are asked, what determines the basicity of amines? The simple reason is the availability of the lone pair of electron on the nitrogen to bond with a hydrogen ion. The availability of the lone pair of electron on the nitrogen atom to bond with a hydrogen ion. That is what determines the availability of, that is what determines the basicity of an amine. Whether it is highly basic or it is less basic. If there is if the electron density on the nitrogen atom is high, if there is high electron density on the nitrogen, making available electrons for donation, then that amine is going to be highly basic. If there is less availability of electron on the nitrogen atom for bonding, then that amine is going to be less basic. However, there are some factors that will determine the availability of, the lone pair of electrons on the nitrogen atom. So some of these factors are what? Some of the factors that will determine the availability of the lone pair of electron on the nitrogen atom to bond with a hydrogen ion are the presence of electron donating alkyl group. When there is an electron donating alkyl group, or electron donating alkyl group on an amine, when there is the presence of an electron donating or electron releasing alkyl group, what happens? These electron donating group are going to do what? They are going to release electron on the nitrogen. Making available more electrons, or increasing the electron density on the nitrogen. So when these electron donating groups are releasing electron on the nitrogen, they are increasing the electron density on the nitrogen and making electron available for bonding, or making electron available to be used for dative covalent bond with a hydrogen ion. And in that case, it gives that amine a high basicity. On the other hand, when there is an electron withdrawing group, what happens? It draws electron away from the nitrogen and making electron less available for bonding. And when it makes electron less available for bonding, what happens? It leads to what? It leads to that compound being, or that amine being, less basic. I'll give an example of this. I'm going to give an example of this. For instance, I want to compare the phenylamine. I want to compare ammonia. I want to compare ethylamine. I want to compare their strength, their basicity. Which one is more basic and which one is less basic? Look at ethylamine here. Phenylamine here. Phenylamine has here the amine group on the amine group on the amine group on the benzene ring is electron doing what? You see, how there's electron withdrawing. Instead, electrons are being drawn away into the benzene ring. Electrons are taken away into the benzene ring. What is happening here is that electrons are taken into the benzene ring. Electrons flow into the benzene ring. The chemistry here is that there is an overlap. There is an overlap of the p orbitals of the nitrogen atom. The overlap of the p orbital of the nitrogen atom with the pi electron system, the pi electron system of the benzene ring. I said there is an overlap of the p orbital of the nitrogen atom with the pi delocalized system of the benzene ring. And this overlapping of the p orbitals of nitrogen and the benzene ring leads to what? It leads to delocalization. It leads to delocalization of the lone pair of electrons on the nitrogen. It leads to delocalization of the lone pair of electron on the nitrogen in the benzene ring, making electrons to be less available for dative covalent bond. So, in this case, when it makes electron to be less available for dative covalent bonds, it makes a phenylamine less basic. It makes phenylamine less basic. On ammonia, if you look ammonia here, ammonia does not have even an electron donating group or an electron withdrawing group. In that case, ammonia remains as it is. Ammonia remains as it is with the lone pair of electron here. It has just the normal two lone pair of electron there on the nitrogen. But on ethylamine, what is happening on ethylamine? What is happening there is that the ethyl group here is all alkyl groups are electron donating. Alkyl groups are electron donating. Alkyl groups are electron donating. So what happens? You see this arrow shows that these alkyl groups are electron donating. They are donating electron onto the nitrogen atom, increasing the electron density on the nitrogen atom. And when they increase the electron density on the nitrogen atom, they make electron pair more available for donation or more available for bonding with a hydrogen ion. I said the ethyl group is electron donating, releasing electron to the nitrogen atom, making electron pair more available for dative covalent bond, and this makes ethylamine more basic than ammonia. So you will see here that ethylamine is more basic because there are more electron on the nitrogen, making there are more electron on the nitrogen which are available for dative covalent bond than in the case of ammonia. And ammonia here, in this case, there's a lone pair of electron on this nitrogen on ammonia. There's a lone pair of electron on this nitrogen on ammonia, still making it basic. Unlike in phenylamine, all electrons have been taken into the benzene ring. Electrons have been flown into the benzene ring as a result of the overlap of the p orbitals of the nitrogen with the pi delocalized system of the benzene ring, and that leads to what? It leads to the electrons, the localization of the lone pair of electrons on the nitrogen in the benzene ring. So these electrons here, as you see the arrow, the electrons here have been moved into the benzene ring. the lone pair of electrons here that would have been used for dative covalent bond has been moved back to the benzoyl ring and are being delocalized there. For that reason, it makes the amine group here, it makes electrons here less available. There are not electrons here that can be used for dative covalent bond, and it makes now the phenylamine less basic. So you see the basicity is increasing. Basicity increases as the number of alkyl groups, electron donating group are increasing. So in that case, primary amines, in that case, we can conclude that the more the alkyl groups, the more the alkyl groups on the nitrogen atom, the stronger the basicity of the amine. Once more the alkyl groups on the nitrogen atom, the stronger the basicity of that amine. For instance, we can conclude that primary amines, we can say this one, we can say tertiary amines are more basic than secondary amine, and secondary amine are more basic than primary amine. The reason is that there are more alkyl groups here that are donating electrons on this, making the electron density here more high and more available for dative covalent bonding. There are two of them here also making electrons here more available for bonding, and there's only one here still making it more available for bonding. So the more the number of alkyl groups on the nitrogen atom, the stronger the basicity of that amine. So now, after doing that, we can now go to the formation of amines. The formation of amines. Amine can be formed from different. There are different ways, the different methods of the formation of amines. There are different methods of formation of amine. Now, the first method is we can form amine. We can form amine from from halogenoalkanes, and this method of formation from halogenoalkane is called nucleophilic substitution. It is a nucleophilic substitution from halogenoalkane. In this case, we will have the reagent. In this case, will usually be a reagent. A reagent in this case, we will have a hot concentrated ammonium, in ethanol. Hot concentrated ammonia in ethanol, we can even call it excess hot ethanolic ammonia. Excess hot ethanolic ammonia. Ammonia in ethanol is usually called ethanolic ammonia. Excess hot ethanolic ammonia. So, and what the method here, the condition usually used here is reflux. We have to reflux it. We heat under reflux. Heating under reflux. You can heat under reflux. That is usually the condition that is used here. Heat under reflux. So now, when you heat under reflux, there is that substitution. For instance, let me give this. For instance, this is an example. I have halogenoalkane, which is bromoethane, which is CH. Let me say CH3. Bromoethane plus excess hot ethanolic ammonia, hot excess ammonia, and that will substitute this one. There will be that. I said it is a nucleophilic substitution. It is a nucleophilic substitution. Why do I say it's a nucleophilic substitution? Because the ammonia is going to be acting as a nucleophile. Because nucleophiles are electron pair donors. There is a lone pair of electron here. Is a lone pair of electron on the nitrogen in ammonia. So when there is heterolytic fission, what happens? The hydrogen goes, the bromine goes, and this one will be donating electron to this one. Here, this one to the will be donating electron there. So now the product from here will be CH3. We will have a CH3, a CH2, NH2, NH2 plus a hydrogen bromide, and this is what I said. This is what we'll call it ethylamine. Ethylamine. But it should be remembered that the hydrogen bromide, which could even react with ethylamine, is removed by the excess ammonia. Because you could be asked why, how. You could be asked in your exam that what is the use of the excess of the ammonium. So you can say hydrogen bromide, because the hydrogen that bromide that formed, and then see excess of the ammonia, something can happen. So we can say hydrogen bromide, which could react with ethylamine, is removed by the excess ammonia. I say hydrogen bromide, which could react with ethylamine. The hydrogen bromide, which could react with ethylamine, is removed. I say it is removed. Is removed by the excess ammonia. Is removed by the excess ammonia. Hydrogen bromide, which could react with ethylamine, is removed by the excess ammonia. So that is how amines are formed from halogen or alkanes using excess hot ethanolic ammonia, or you can say hot concentrated ammonia in ethanol, by heating under reflux. Another method that we can use in the production of in the production of amine, is by reduction. We can produce it from nitriles, and the method we can produce it from nitrite, and the method is by the reduction of nitrile using lithium tetrahydroaluminate 4 in dry ether. I said the method is we can do it from nitriles. We can produce it, or we can prepare it from nitriles through reduction of nitriles using LiAlH4, lithium tetrahydroaluminate, in dry ether. And this is how the condition there is. The condition here is still is by heating under reflux too. Condition is heat under reflux. It is the same thing, heat under reflux. That is the condition, heat under reflux. But here there are about 5 steps. There are about 5 steps in this production. There are about 5 steps in this production. Step number 1 in this production. See, this is step number 1. And step number 1 in this production, step 1. Let me say step 1. In step 1 in this production, we have to heat the halogenalkane. It is from halogenalkane. We have to heat the halogenalkane with what? With with potassium cyanide in ethanol under reflux. So the step 1 is heat the halogenalkane. Heat the halogenalkane with potassium cyanide. Heat the halogenalkane. Heat the halogenalkane with potassium cyanide. You know, potassium cyanide is going to give us the cyanide ion in ethanol. In ethanol under reflux. So this is just how the whole thing is going. This is how you can. This is just how the reaction is. You will see it like this. You will see CH. We are using. Let's use let me say CH3 plus CN. We say it is by heating, and there is that substitution. That substitution, we will have CH3, CN, and plus a bromide ion. So this is a nitrile. The nitrile has been produced. Then I said by reduction of the nitrile, we are going to produce it from nitrile. We must first of all produce the nitrile, heat the halogenalkane with potassium cyanide in ethanol under reflux. In that case, we are producing the nitrile. Then step 2, we have to reduce the nitrile. Step 2. Step 2, reduction of the nitrile. We have to reduce the nitrile. Reduction of the reduction of the nitrile. Reduction of the nitrile using what? Using the lithium tetrahydroaluminate. Using this in dry ether. Using this in dry ether. So in that case, when you are using this, you can even using this in dry ether, or you use hydrogen. You can use hydrogen with nickel catalyst. You can use hydrogen with nickel catalyst. But this lithium tetrahydroaluminate help to provide us the hydrogen. So see how it works. It helps to provide all the nitrogen. See how the equation is going to work here. Let's see how we can reduce this. The reduction here is, we are going to reduce this one. That is CH3, CN. Okay, a reduction is what? Addition of hydrogen. Reduction is addition of hydrogen. So this is going to lithium tetrahydroaluminate in dry ether is the source for our hydrogen. So it is our hydrogen. Our hydrogen is required. 4 hydrogens are required. In this case, 4 hydrogen are required to give what? To give us CH3. CH3, because we have to convert this carbon here, because there are 2 carbons here. This is a nitrile. This is a nitrile. So we need to have 2 hydrogens. 2 hydrogens there. So in that case, it will be CH2. CH2. Then we need another 2 hydrogen for the amino group. CH2, NH2. And that's why I say we need 4 hydrogens. Then another method of production of the production is from reduction of amide. We can produce amines from amides. You know, amides, they contain a methyl group. Amide, they contain a carbonyl group. They contain a carbonyl group. So reduction of amide, they contain a carbonyl group and an amino group. So now reduction of amide, we will still use this lithium tetrahydroaluminate, LiAlH4, lithium tetrahydroaluminate in dry ether. It helps to provide us what? Our hydrogen. So for this reduction here, we are going to use amide, and a good example of this amide here is let's use CH3. Our CH3 is amide. I say an amide contains a carbonyl group and an amino group. Then we will need again 4 hydrogens. We will need 4 hydrogens, and these 4 hydrogens are going to do what? There will be a CH3 here, converting this to CH2, removing of the oxygen. I'll put H2, CH2, then NH2, plus our 4 hydrogen. 2 of the hydrogen have been added here. This molecule, this oxygen atom here has been removed, and the 2 of the hydrogen will be used for this in the formation of water. So plus a molecule of water. So in that case, the amide, the carbonyl group here, this carbonyl group here, the carbonyl group here in this group, in this amide, is reduced to what? Is reduced to ethylamine. So it should be noted that the the carbonyl group, this is a carbonyl group here, the carbonyl group the carbonyl group here, this is the carbonyl group here, is the carbonyl group in the amide. The carbonyl group in the amide is reduced to ethylamine. The carbonyl group in the amide is reduced to ethylamine. This is ethylamine here. There are 2 carbons there. That is how you can do that. That is the simple. They say that is a very simple way of doing it. That is a very simple way of doing it. Then there's another. There's the last method. The last method that we can use in the formation of amines is producing amine from phenyl. Producing it by the reduction of nitrobenzene. We will do it by the reduction of nitrobenzene. So formation of phenylamine is by the reduction of nitrobenzene. So reduction of nitrobenzene. So in this case, nitrobenzene is our reagent, our reduction of nitrobenzene. Our reagent here will be a reagent. Our reagent in this condition will be what? We will have concentrated hydrochloric acid, and tin, and the tin metal. We will have concentrated hydrochloric acid and tin. And the condition in this reaction will be what? Our condition here, will heat under reflux. All this heating under reflux. Heat under reflux. Heat under reflux. You have to heat this under reflux. So in this case, you will have to heat the nitrobenzene. Heat the nitrobenzene under reflux with tin. And the concentrated hydrochloric acid. I said heat nitrobenzene. You have to heat nitrobenzene. Heat nitrobenzene under reflux. Heat nitrobenzene under reflux with tin. Tin is SN. With tin and concentrated hydrochloric acid. You have to do that. And if you do that, what will be the product? This is the product. See the reaction. Let me show you how the reaction is going to go. The reaction here will be, this is nitrobenzene. This is nitrobenzene. I said by reduction. I say a reduction. And in reduction, we will need hydrogen. Yeah, there's going to be 6, not 4 this time around. And we will have this phenylamine is produced. This phenylamine plus 2 molecules of water. We call this a phenylamine. Phenylamine. And that is how you can do that. I say you heat this under reflux. So heat nitrobenzene under reflux with tin and concentrated sulfuric acid and concentrated hydrochloric acid. And that's what you are going to have. So that there are 4 methods. Once more, there are 4 methods that are used in the production of amine. I said the first method for the formation of amine, the first method is from halogenoalkane by what? Nucleophilic substitution. The second method is from nitriles, and that is by reduction of nitriles. You have to produce the nitrile first, then use lithium tetrahydride to illuminate in dry ether to reduce it to ethylamine. The third method is by reduction of the amide again, and by the reduction of amide, the carbonyl group in the amide is reduced to ethylamine. And the fourth method is by the reduction. The fourth method is by the reduction of nitrobenzene, and the reagents are what? Concentrated hydrochloric acid and tin. And all this is you heat it under reflux. There are other reaction of phenylamine. There are other reaction of phenylamine. Remember that reaction of phenylamine, which are electrophilic substitution. The electrophile will substitute the hydrogen on the nitrogen. The electrophile will substitute the hydrogen on the benzene ring. So this is what is going to happen. Remember, there's one thing. The amino group with this group, and the OH group, and this OH group are this group, this and these groups. These groups are electron donating. These groups are electron donating groups. They are electron donating group. They are electron donating group. So when you start reacting, when you start reactions with phenyl compounds, or let me say phenylamine, or phenols, any compound, when you start doing compounds with aromatic compounds, reaction with aromatic compounds, you should be aware, or you should know the groups that are electron donating and the position that they are directing. For instance, the amino group and the OH group are electron donating. They are electron donating. These groups are electron donating. Electron donating. They are electron donating, and they are electron donating and they are 2, 4, and 6. They are 2, 4, and 6 directing. So this group, the amino group and the OH group are electron donating. They are electron donating. And in that case, they are also 6. Yeah, sorry. They are 2, 4, and 6 directing. Let me put it clearly. And 6 directing. So in that case, any incoming group, they will direct it to the 2, 4, and 6 position on the benzene ring. So now the extra electron density in the benzene ring. There's one thing I want you to know, that the extra electron density in the benzene ring makes it to be attacked by electrophiles, because you could be asked, what property makes benzene to undergo electrophilic substitution? What property makes benzene to undergo electrophilic substitution? You can say the extra electron density. The high electron density in the benzene ring makes it to be attacked by electrophiles. You know, electrophiles are species that they love electron-rich centers. They love to go towards electron-rich centers. They are electron deficient. Electrophiles are electron deficient, so they would like to move towards electron-rich centers. So for that purpose, I am saying that Because this group are what? This group are electron donating. They will donate electron to the benzene ring, making the benzene ring to have a high density of electron. And because of the high extra electron density in the benzene ring, it makes the benzene ring to be attacked by electrophiles. For instance, let's write this reaction here. For instance, this reaction here for phenylamine phenylamine. You should know quite all right that this is it should be noted that this is the first position, this is the second position, this is the third position, this is the fourth position, this is the fifth position, and this is the sixth position. This is the first, this is the second position, this is the third position, this is the fourth position, this is the fifth position, and this is the sixth position. And since we said they are electron donating, this group, the amino group and the OH group are electron donating. Now the amino group is here. Amino group is going to flow electrons here. All electrons are going to move here. All electrons here. The lone pair of electrons on the nitrogen, all of them are going to flow into the benzene ring. There's going to be delocalization of electrons in the benzene ring. There's going to be high density of electrons in the benzene ring. For that purpose, electrophiles will want to move towards the benzene ring. Electrophile will want to attack the benzene ring, and when they are about to attack the benzene ring, this group is going to direct them to which position? It will either direct them to this position, which is the second position, directing them to the fourth position, and again to the sixth position. So in that case, let me just go ahead. I will not wipe the positioning. I just want to put it so that you can, learners can better understand it. Plus bromine, plus bromine. So it is 2, 4, and the 6 directing. It means we need 3 bromine. There will be 3. Yeah, let me put this. Yeah, this is what is going to. This is what is going to happen. We will have and in that case, they are going to substitute this, the hydrogens here. The hydrogen here, the second position. On the second position, we will have it here. On the fourth position, we will have it here. And on the sixth position, this is what we'll have there. So these are the product that we are going to have here as a result of this. We will have bromine here. We will also have bromine here. I will also have bromine here. I said 2, 4, 6. 2, 4, 6. And these are the positions. Fellow learners, for phenols, that is a benzene ring and an OH group on it, it will also be, they are also what we call electron donating. It will still follow this pattern of reaction. The same reaction method here will be the one in phenols too. They are electron donating, and it will be 2, 4, and 6 directing, like in this one. And here we can call this compound, 2 We can call the compound 2, 4, 6. How many bromines are there? There are 3 tribromo what? What was the compound? Phenyl amine. That is the compound. So because it is 2, 4, and 6 directing, and it is electron donating. So as I said once more, this is electron donating. It is going to donate, the lone pair of electron and nitrogen is going to flow, but into the benzene ring. There's going to be localization of this bond here, of these electrons in benzene. This gives benzene a high density of electrons. And because of the high density of extra electrons in benzene, it makes benzene to be attacked by electrophiles. And a good electrophile will be the bromide, which will go to substitute the hydrogen on the 2nd, 4th, and the 6th position, resulting in 2, 4, 6 tribromo phenylamine. Another reaction of phenylamine is the reaction with we call it diazotization, the making of azodide, diazotization, the making of azodide. Diazotization is the reaction between phenylamine and nitrous acid to give what? A diazonium salt. We said it reacts, phenylamine reacts, we say phenylamine reacts with a nitrous acid that is HNO2 NO2 to give what? To give a diazonium salt, a diazonium, to give a diazonium salt. Remember that this salt is very, very, very unstable at the low temperature, at a temperature below 10 degrees. This salt is very, very unstable, and when heated with water, it will now decompose to give hydrogen. Okay. So to give the diazonium salt, that is the first step to give. Diazonium salt. Then the second step for this, so phenylamine will react with nitrous acid to give a diazonium salt. This is the reaction. Yeah. So for that purpose, we will have the diazonium salt. In the first case, this is what happens for the reaction to occur before the formation of the diazonium salt. Prior to the reaction, we will have this reaction. We will have sodium NO2 plus HCl to give the nitrous acid. Plus the sodium chloride. Then step 1 of this reaction is when the phenylamine will react with nitrous acid. So let me say step 1. In step 1, production of benzene diazonium chloride. production of benzene, disonium chloride. That is the chloride. Production of benzene disonium chloride. This is the salt I'm talking of, disonium salt. And this is where the reaction salt at a temperature what? Temperature. The temperature is usually less than 10 degrees Celsius because the salt will decompose to give what? Will decompose to nitrogen if the temperature increases. So it is usually below 10 degrees because the salt will decompose. So now this is the reaction. When that happens, this is the reaction. Phenylamine will react with the nitrous acid to give the salt. This is phenylamine. Phenylamine, this is it. Plus the nitrous acid. And that plus the hydrochloric acid. And what will be formed will be the benzene disonium salt. This is the benzene disonium salt that we are talking of. Benzene plus water, I say plus. So this is what happens here. There is a nitrogen. This is the salt. The salt is, let me show how it is. We have 1, 2, and 3. That is the salt. Then nitrogen again, and chloride. Let me put this here. The charges. So this is the salt. This is the salt. This is what I call the salt. This is what I call the benzene disonium chloride. Disonium chloride. Benzene disonium chloride. That is the salt. Then step number 2 in this very reaction. Step 2 in this reaction. In step 2 in this reaction, the disonium ion reacts with an alkaline solution of phenol. And in this reaction, we call it coupling reaction. So a coupling reaction is a reaction when a disonium ion reacts with an alkaline solution of phenol. Okay. Disonium, we say disonium ion reacts with an alkaline solution of phenol. Alkaline solution of phenol in a coupling reaction. So this is what we call a coupling reaction. Reaction of the diazonium ion and an alkaline solution of phenol. So this is the reaction. From this reaction, you are going to see how the dye is going to be formed. We are going to have this. Oh, see there. 1, 2, 3. Yep. Okay. Plus this is a coupling reaction. Diazonium ion and an alkaline solution of phenol. And this will be our product. The product here will be let me use this. We have a plus here. Okay. We will have this plus HCl plus HCl. We call this this product here azo we call it azo dye. The mechanism is not really needed. But if you really want, you may want how this came about, because you could still be given the equation to write for purpose of revision. This is how you can do it like this. You can put it like this. You put it like that. Okay, the nitrogen. Nitrogen. Okay. There is a plus here. There is a minus here. And it should be recalled that there is a movement of electrons here. Because there is going to be a heterolytic fission. This will be the product. It's the same product. Apply hydrogen chloride gas. That is the source of the hydrogen chloride gas. So that is the source of the hydrogen chloride gas. As you see it like that. So that is just this. So I'm saying that the azo dye is a colored compound formed on the addition of phenol to a solution containing a diazonium salt. An azo dye is let me say, an azo dye is a colored compound. It's a colored compound formed. It's a colored compound formed on the addition of phenol. On the addition of phenol to what? To a solution. To a solution containing a diazonium ion or a diazonium salt. So that is an azo dye. An azo dye, it is that is the whole thing. So an azo dye, please. An azo dye is a colored compound formed on the addition of phenol to a solution containing a diazonium ion. So that is how you can prepare it. So that is just all for now for regarding the amines. In the next video, I will be giving you amino acids. I will be treating amino acids. So a recap of our topic today. A recap of our topic today. We have just treated amines. I said there are three categories of amines, and we have primary, secondary, and tertiary, depending on the number of hydrogen atoms that are substituted, the number of hydrogen atoms on nitrogen that have been substituted. And we gave examples of primary amines. We gave an example of primary amine, and showing that only one of the hydrogen atom on nitrogen was substituted. Then the secondary amine, we gave examples that of the two hydrogen atoms that have been substituted. And then our tertiary amine, we gave example of 3 hydrogens that have been substituted. We went on the basicity of amine, that the basicity of the amine will depend, or the strength of the amine will depend on the availability of the lone pair of electron on the nitrogen, on the availability of the lone pair of nitrogen, the lone pair of electron on nitrogen for bonding. And we said in amines where there are electron donating amine that have electron donating alkyl groups, those alkyl groups will donate electron or will release electron on the nitrogen, and nitrogen, there will be high density of electron on the nitrogen available for dative covalent bonding, and for that reason it will make that amine to be highly basic. On the other hand, when there is electron withdrawing group, or like in the case of phenylamine, what happens is that the electrons will flow into the benzene ring, leading to the localization of the lone pair of electron on the nitrogen in the ring. The lone pair of electron in the nitrogen will now be delocalized, but in the benzene ring, and the electrons making electron not available. There will be electrons making electron not available or less available on the nitrogen for what? For dative covalent bond. And for that purpose, when electrons are less available for coordination or for coordinate bonding with a hydrogen ion, that amine become less basic. Then we had to compare them from phenylamine and right to the ethylamine, and ethylamine is the most basic amine because of the presence of the electron donating group. Then we say the more the number of electron donating group on the nitrogen, the more the number of electron donating group on the nitrogen. For instance, in tertiary amine, it makes it to be more basic than secondary amine and than primary amine. So in that case, the more the number of hydrogen electron donating groups, what happens? There's going to be more electron release on the nitrogen. There's going to be more electrons are going to be made available for what? For dative covalent bond with hydrogen ion. And for that purpose, that substance or that amine is going to be highly basic. Then we went further. We went further for the formation of amine from halogenoalkanes. There are 4 methods that we can form them from halogenoalkanes, and that is nucleophilic substitution. And from nitrides. In that case, we have to form the nitride and then through reduction of the nitrides using lithium tetrahydroaluminate in dry ether. Then the third method of the formation of the amine is a reduction of amide, still using lithium tetrahydroaluminate in dry ether. And then the fourth one was what? By reduction. The third one is reduction of nitrobenzene. Reduction of nitrobenzene into phenylamine. We went further into the reaction of phenylamine and that we said phenylamine will undergo electrophilic substitution, substituting the hydrogen on the benzene ring. Why do you think that phenylamine will undergo electrophilic substitution? We gave the reason that because of the high extra electron density on the benzyl ring, it makes the benzyl ring to easily attack, or it makes the benzyl ring to be attacked by what? By electrophile. Remember that electrophile are electron deficient species, and the benzyl ring has a high density of electrons. So they want to go towards electron rich centers. So because of the high density in the benzyl ring, it is subject to electrophilic attack. And for this purpose, the amino group, for the purpose of revision, the amino group and the OH group are electron donating, and they are also 2, 4, and 6 directing. For that purpose, the phenylamine is going to be 2, 4, 6 directing. And in that case, because since it is even, it is electron donating, is going to increase the density of electrons in what? On the benzyl ring. Because it's going to increase the density of electrons in the benzyl ring, now benzyl ring is going to be subject to electrophilic attack. For that purpose, reaction with bromine is going to be what? It's going to be 2, 4, and 6 directing, leading to what? Leading to 2, 4, 6 tribromo-phenylamine. That was the product. And then we went again for the reaction of diazotization. That is the formation of azodide. Diazotization reaction of the phenylamine with nitrous acid. In the first case, I told you that we have to first of all get the nitrous acid get the nitrous acid. Then now react the nitrous acid with the phenylamine, and it will lead to a benzene diazonium chloride. This benzonium diazonium chloride can now react with an alkaline solution of phenol, and we call it the reaction between diazonium ion with alkaline solution of phenol. We call that type of reaction a coupling reaction. And when it reacts like that, the resultant or the product form is an azodide. It's an azodide. I've given you the equation, and I went further to show you how the reaction is taking place, the mechanism that is taking place there. So once more, I said an azodide is a colored compound that is formed on the addition of phenol to a solution containing a diazonium salt. In our next edition, we will be treating amino acid. Thank you once more for watching. Thank you for watching. Those of you who haven't subscribed to our channel, please take your time and subscribe. Take your time and subscribe to our channel, but do not go without hitting the notification bell. Thank you. Wishing you all the best in your exams.